Today, we're diving into a fundamental chemistry technique, acid-base titrations. But we're not just going to go through the motions. We're going to see how a simple graph, a titration curve, actually tells a fascinating story about what's happening molecule by molecule.
So let's set the stage. Imagine you're in a lab and you've got this beaker of acid. The problem is you have no idea how concentrated it is. How would you possibly figure that out? This isn't just a textbook problem, it's a huge deal in everything from making medicine to ensuring food quality.
Well, chemists have this incredibly elegant method to solve it, and it's called titration. The big idea is actually pretty simple. You take a solution you do know the concentration of, we call that the titrant, and you carefully, drop by drop, add it to your mystery solution until, boom, you hit a perfect chemical balance. Then, by seeing exactly how much titrant you used, you can work backwards to find the concentration of your unknown.
To get the hang of this, our first story is the classic tale. A strong acid, hydrochloric acid, going up against a strong base, sodium hydroxide. This is the most straightforward case you can get, and it gives us the perfect baseline for understanding everything else. So let's follow the journey of the pH in our beaker at 4 key moments. We'll start with just the acid, then we'll add some base, then we'll add the exact amount of base needed for neutralization, and finally, we'll see what happens when we go a little overboard. Let's see what story the curve tells us. All right, at the very beginning, before we've added a single drop of base, our beaker is just full of hydrochloric acid. And since it's a strong acid, it completely breaks apart in water, which gives us a very low superacidic starting pH of exactly 1.00. Okay, now we start adding our strong base. The base starts to neutralize the acid, so the pH begins to creep up. But look at how slowly it's moving. It's a really gradual climb. We've only gone from a pH of 1 up to 1.48, even though we've already added half the base we're going to need. And here it is, the climax of our story, the equivalence point. This is that perfect fleeting moment when the amount of base we've added is exactly equal to the amount of acid we started with. Everything is perfectly neutralized. So what do you think the pH is at this critical moment? Bam! It's exactly 7.00, perfectly neutral. And why is that? Well, when a strong acid and a strong base react, the only things they make are water and a neutral salt. In this case, just plain old table salt, sodium chloride. The solution isn't acidic anymore, it isn't basic, it's just neutral. This is a dead giveaway of a strong titration. So what happens if we just keep adding base past that equivalence point? Well, now there's no acid left to fight back. Any extra base we add just builds up, and the solution becomes strongly basic, like really fast. The pH just skyrockets all the way up to 12.30. Okay, that was the simple story. But what happens if we change one of our main characters? Let's get to our next tale. This time, instead of a strong acid, we're going to use a weak acid, acetic acid, the stuff in vinegar, against that same strong base. As you're about to see, this changes the plot a lot. And right off the bat, we see a huge difference. The starting pH is 2.87. I mean, it's still acidic for sure, but it's way higher than the 1.00 we got with the strong acid. And that's because weak acids are kind of stingy with their protons. They don't fully break apart in water, so there are just fewer acid ions floating around at the start. Now, here's where a totally new feature shows up on our graph, the buffer region. See how flat the curve gets? As we add base, the acetic acid turns into its partner molecule, its conjugate base. When you have a good mix of both in the solution, it creates this amazing chemical shock absorber, a buffer, that fights against big swings in pH. And there's a really special spot right in the middle of this buffer region called the half equivalence point. It's when we've neutralized exactly half of the weak acid. At this one unique moment, the pH of the solution is equal to something called the pK of the acid, which is kind of like a chemical fingerprint. For acetic acid, that's 4.74. Okay, we've made it back to the equivalence point. We've added just enough base to react with all the weak acid. But remember that plot twist I mentioned? Here it comes. Is the pH going to be 7 this time? Nope, not even close. It's 8.72, which is definitely on the basic side. And here's the crucial reason why. When all the weak acid is used up, what's left behind? Its conjugate base, acetate. And it turns out acetate is a weak base itself. It reacts with water to create a few extra hydroxide ions, and that's what pushes the pH above 7. All right, so we've just watched two very different stories play out. Let's do a little showdown. Let's put their titration curves side by side and really nail down the key plot points that tell us who's who. This table really sums it all up. The weak acid starts at a higher pH, and it has that unmistakable flat buffer region. But the biggest clue? Its equivalence point is basic, not neutral like the strong acids. The only place their stories are the same is way at the end, after the equivalence point, where in both cases, the extra strong base we've added just takes over and runs the show.
Okay, this is all great on a graph, but there's one tiny problem. In a real lab, you can't see the pH. The equivalence point is a totally invisible chemical event. So how on earth do chemists know when they've hit that sweet spot? Well, they need a secret decoder. And that secret decoder is something called an acid-base indicator. These are these really cool molecules that have a special superpower. They change color at a very specific pH. By adding just a couple of drops into our beaker, we get a clear visual signal that tells us, hey, you've reached the end.
So how does this magic work? Well, the indicator is actually a weak acid itself. In its acidic form, it has one color. Let's say it's colorless. But when the pH gets high enough, it loses a proton and changes into its basic form, which has a totally different color. Let's say pink. The pH of the solution decides which form is dominant, and that's the color we see. But here's the catch. You have to pick the right tool for the job. You can't just grab any old indicator. Let's look at two common ones. Methyl orange changes color down in a really acidic range, around pH 3 to 4. Phenolphthalein, on the other hand, changes color up in the basic range, from about pH 8 to 10. So, for our weak acid titration, which one do we pick?
And this is where it all clicks into place. Remember, the equivalence point for our weak acid titration was 8.72. Well, look at phenolphthalein. Its color change range, from 8.3 to 10.0, perfectly surrounds our target pH. This means it will go from colorless to pink right as the pH makes that massive vertical jump on the graph, giving us a super sharp and accurate signal. If we'd used methyl orange, it would have changed color way too early, long before we were even close to being done.
So just by plotting pH against volume, we were able to read a whole story about an acid's identity, its strength, and how it behaves. It really makes you wonder, doesn't it? What other incredible hidden stories are just waiting to be told inside the data and graphs of science?